Okay, so now we're ready to learn about momentum analysis. Remember that momentum analysis comes from a rearrangement of kinematics and force analysis into a useful form for certain special cases, which you'll see. Just go with this. Notice the connection. Notice that it's not really that new, it's a new rearrangement. So these are derivations that you should be able to show on an exam. Maybe it'll be 10 points. I'll do a kind of quick and dirty, nice notation, leaving out varying masses. You can look up in textbooks or elsewhere more general derivations, but this gets to the heart of it, and I think it's good to do it this way. So it's the impulse momentum or impulse momentum relation. Really, it's the net impulse causes a change in momentum. This is just, keep this in mind, this is just a convenient rearrangement of Newton's second law. Right? So that's what we start with. Usually we'll focus on a single object when we use this. We'll look at one object, other objects are interacting with it. So let's start with Newton's second law. Here we go. The net force vector, force is a vector. This is all the interactions on our object, our receiver, whichever one we're choosing to look at. The net force. That causes the acceleration of that thing. Mass of the object or the receiver resists the acceleration. So that's Newton's second law. Good. And again, we can break that into x and y components. Now, by kinematics, the acceleration is defined as the rate of change of velocity vector of r. So I just make this move, put a in terms of dv dt vector. Again, this is not a force, right? This is not an interaction. The interaction's over here. They cause the change. Now, let's rearrange this as an integral. You saw this when we were doing the derivation of the constant acceleration equations for kinematics. Let's rearrange this as an integral. You can kind of cheat and think of moving the dt over here, and you'll see some new notation that I've said. The net force vector on r times time, or dt, integrated over that interval. As I mentioned before, usually this is for quick interactions, collisions, explosions. And so I'm introducing this notation, JB, and I find it very useful. Before I said earlier to later, but just to point out that this is usually useful when you have it just before an explosion or collision and just after. So JB and JBA, that's the time interval for which this interaction occurs. Net force. That causes, well, if I move the dt over here, I'm left with that. So the integral, mass of the receiver, dvr of the receiver, from that just before and just after. Once you see that that is a rearrangement of Newton's second law, from this derivative form to an integral form, you're in business. So first, notice that if I integrate that, I'm leaving the mass constant. Mass does vary for things like rockets, even the exhaust pipe of a car, if you were to worry about that. So I pull that out of the integral. The integral of dvr is just a change in v of that object. So what do I have? I've got this thing causes this. I'm going to rename it the net impulse on r vector, net impulse, j or capital I vector, causes. We're going to call this the change in momentum of r. P, it's interesting to try to find the history on why that's labeled P, but don't worry about it. You run out of letters real fast, right? Change in P with a vector of r. Net impulse interaction on r causes a change in momentum of r, where P of r is defined as the mass times the velocity of that object. So there you have it. Do you see the connection? Notice how that is a quick step right over to our rearrangement, which we're now giving new names. Seems more confusing than it is. Net impulse causes change in momentum. Why is it useful? Well, the utility really flies in this short interaction time. So let's go over here and I'll point a couple things out and demonstrate that. We said last time useful for short-time interaction, collisions, explosions. So we've come up with, by that rearrangement, we've come up with this grouping of terms, mass times velocity. And we've given it a name, momentum. Momentum. Something's got momentum if it's going fast and it has a lot of mass. It's got more momentum. Okay, so you get that idea. However, direction matters. So something going away from you, hey, no problem. Something coming towards you, like a rhinoceros, that's a problem. Okay, so we've got to deal with direction. Impulse, again, falls right out of the rearrangement as J is a force over time. Now notice here, each object that interacts with our receiver, I called it A here, might have an impulse. If there's lots of impulses, it's going to be hard, and usually you won't go here because you use the best analysis tool you can. But if there's lots of them, you can't just take one. You've got to take the net impulse from all the interactions on our receiver. Again, this force over time. If you've got an equation here, you can integrate it fine. Just before to just after, usually. If you know the average force, then that's the time between just before and just after. Or if you've got a curve of force over time, then it's going to be the graphical area between the curve and the t-axis. Okay, so we've done it. We have derived the net impulse in a very quick step. Again, you have to do problems to realize what we've done and what we've achieved and how cool it is for particle physics or for collisions on the freeway if you want to measure things out. A variety of things. All right, so take another quick look over here. And I want to point this out again. These are vectors, and people often forget this. So we have two cases often. As you're getting introduced to it, we do simple problems, one-dimensional problems, and then direction must be included as plus or as minus. If you don't include that, it doesn't make any sense. You've got just before and just after. So A coming in and hitting R. So R is the guy that I'm looking at here. That's my one that I choose. Now I could look at A, so you could analyze it however you want. You've got to make a choice, and that's maybe stated in the problem, or you look at R and then separately you look at A. So you do them one at a time, divide and conquer. And what happens here is there's a collision, and so this I like to say is during. And that is messy. I don't know exactly what the forces are. Can you model those forces on a collision? You can model them. Do you know exactly what they are? I don't know. The beauty is we can look at just before and just after. There's some force over some short time. And so, however, there's different ways to deal with that. Or you can break the momentum and impulse up into x and y components in 2 or 3D and do each direction separately. The net impulse on R in the x direction causes a change in momentum of that object in the x direction. The net impulse on R in the y direction, all the y components of the impulses, equals a change in momentum in the y direction. Got it? So you have to deal with direction. 1D plus or minus, 2D, break it into components. Impulse is a vector, momentum is a vector. All right? And that's how we deal with it. Now, in order to actually do this, there's two things to realize. This is your tool, so just think. If you know the change of momentum, you can know what the impulse is. But change of momentum is not impulse, just like MA is not a force. Impulse is an interaction. This is what happens. This is causality. Causes. This causes that. Okay? So the impulse, if you know the value of that, then you know the value of that. Okay? So let's take a look real quickly, too, at our units. Well, real roughly, that's force times time, isn't it? That's a Newton times a second, for example. What's this? Momentum. Change of momentum. Same thing. That I've got a kilogram meter per second. Mass times velocity. Hey, a Newton, that's like MA. So that's a Newton is like ma, meter per square, kilogram meter per second squared times a second. And wait a minute, those go away and I end up with kilogram meter per second. So yes, they have the same units, just as force has the same units as ma. But force is an interaction, ma is not. Impulse is an interaction. Momentum, change of momentum is not an interaction. It's what happens to it. Same units though, right? And there's no special name. So we just call it kilogram meter per second. You can use grams, centimeters, hours, years, whatever you want to use. You can use that, but there's no special name given to the unit for momentum, which is also the unit for impulse. Okay? I think we are running short on time. Is that kind of doing okay? So that's the theoretical structure. Okay? We're going to take a look at some examples in play in just a moment. Remember, Newton's second law, rearranged. We keep the causality, but we do rearrange it. And we kind of take the dt over here and make sure you write that out. Use good notation. And then whatever you're given, you're given. If you're given this, you can get that. If you're given that, you can get that. Whatever you get. If you've got a bunch of forces, it's a little bit more of a pain. If you've got a graph, you've got area underneath it. So get acquainted with them. That's the task before you, and do lots of problems and keep that straight. But realize, hey, this is Newton's second law in disguise. Okay. Now we're going to look at conservation of momentum and some examples.